Hello, this is Ollie Collins, and this is my video going over homework assignment number 8, the knapsack problems. So first up, what you see on my screen is my code for task number 1, where we just implement the basic 0-1 knapsack algorithm. Uh, so I'm definitely going to try to keep this short. I know I said that last time, and it was a long video, so I'm going to try my best here, but we import, util array list. This is our class knapsack. We have a main method that contains our problems given example values, and the main method calls our actual knapsack solver. So media below, here's our knapsack solver. As the problem statement asks for, we validate a bunch of stuff as far as the inputs go, and make sure there's no weights or no values, that the lengths are the same. There's no funny negative values or anything like that going on. So that's what all those if statements are doing there. And then we actually get into creating our dynamic programming array. So I'll go into a lot more in detail in my written report. So in the effort to try to keep this video short, as I said, I'm going to try and breeze through this. So essentially the way we're going to create our two-dimensional table, which if you notice here, that's what this statement here is doing, is we're going to use two for loops. And to show what these two for loops are doing, I'm actually going to go through the output here in a second. But yeah, we have two for loops. Those will populate our dynamic programming table. And then this code here will actually find out which specific items actually led to that maximum value. So that's what all this code is doing and printing stuff out. And then here's our helper method that actually helps print these intermediate algorithm iterations. So let's go back up to our for loops. In general, we see that we can reach a maximum value of 120, and the items that lead to that maximum value are item 2 with a value of 100 and item 3 with a value of 120. They have a weight of 20 and 30, which is a total weight of 50, which is precisely what our maximum capacity is. So I'm glad in this problem and in prior homework assignments like these search algorithms, you encouraged or even required us to print out intermediate iterations of each algorithm, because that really helped me understand what was going on with these DB tables and how this was all working together in order to solve these problems made a lot clearer. So basically, the way this knapsack problem is solved is we're going to create a DB table. So our rows are going to be, starting from 0 all the way to 3. So that represents, item 1, item 2, item 3, or taking 0 items. And then here are the columns. I've only shown multiples of 10, but it'll be multiples all the way to 50. Or not multiples, it'll be, 0, 1, 2, 3, all the way up to 50. So essentially what this first iteration is doing, or this first row, it's saying, okay, if we choose 0 items, and these are different capacities, if we choose 0 items, what's the maximum value we can get? Well, clearly, if we don't take any items, the maximum value will always be 0. The same thing for the columns. If our total maximum capacity is 0, then we can't pick any items. That's why all these first columns are full of zeros as well. So that's kind of like the base case that gets us started. Then we move on to the next iteration of our for loop, and we get into the second for loop here, which is starting to populate this row with values. So this first entry is saying, if we have a maximum capacity of 10 and item 1 has a weight of 10, can we include item 1? Of course, the maximum capacity is 10, item 1's weight is 10, so we can include it in our bag of stuff. So item 1 has a value of 60. So the maximum value, if we have a capacity of 10, it can choose either no item or 1 item, is 60. And we see the capacities increase from here. So of course, with a maximum capacity of 30 and item 1 weighs 10, we can include item 1. So this is kind of the next simple case. Then we move on to the next iteration. So this is saying, okay, for various maximum capacities, what combinations of items, either no items, item 1, or item 2, or item 1 and 2, can we include? So if we have a maximum capacity of 10, item two's weight is 20, so we cannot include item two in our bag. So what the algorithm does is it looks immediately above, or the cell immediately above, which is 60, and puts that value there. Moving on to a capacity of 20, item 2 has a weight of 20. We have a maximum capacity of 20, so therefore we can include item 2 in the list if we. The question is if that is most optimal. So item 2 has a value of 100. So if we include item 2 in our bag, we get a value of 100, and the weight of item 2 is 20. Our maximum capacity is 20, so 20 minus 20 means we have 0 leftover capacity, so we'll go up one row, go over here to 0, and we see we can't add any more items, which is expected. Item 2 is taking up all the capacity. So what this now shows us, if we include item 2, we get a value of 100, but we also know for a maximum capacity of 20, we can just include item 1 with a capacity or a value of 60. Well, 100 is greater than 60, so we're going to choose to do item 2. If we go up to a maximum capacity of 30, we see item 2 again has a weight of 20 and a value of 100. So 30 minus 20 means we have 10 capacity left over if we do choose to include item 2. So if we include item 2, we have a capacity or leftover capacity of 10. So we'll go up one row, go over to 10 and say, hey, even with a leftover capacity of 10, we can also include item 1. Item 1 has a value of 60, so 100 plus 60 is 160. And then we compare this to the prior maximum value you got for capacity of 30, which was just including item 1. So that's 60. 160 is greater than 60. So we know with a capacity of 30, and if we have to choose some subset of either 0 items, 1 item, or item 2, we can actually achieve a maximum value of 160, and that's got by choosing both item 1 and 2. And of course, for maximum capacity of 40 on to 50, we can again choose both item 1 and 2 and get a maximum value of 160. So essentially, we're recursively building up this table. So we're starting from the base cases for various capacities. We're trying to find, what's the maximum value we can get from combining previous items. And then as we get further on, we see, hey, if we include this item, we'll have some leftover capacity. What's the best we can do with that leftover capacity, which is what all our prior work has already found for us. So we look at item 3. If the maximum capacity is 10 and a weight is 30, then we can include item 3. So we go back up above one cell, and we see that the best we can do is get a maximum value of 60. So we'll just copy that down. Go up to a value of 20, or maximum capacity of 20. We see the weight is 30, so we still can't fit item 3 in our bag. So we'll go up one cell. It's like, hey, with a maximum capacity of 20, we can actually get a value of 100. Now, if we go to a maximum capacity of 30, we see, hey, the weight of item 3 is 30. So that means we can put item 3 in our bag. So the value of item 3 is 120. So we can get a value of 120 if we put item 3 in our bag, and item 3 weighs 30. So maximum capacity of 30, 30 minus 30 is 0. So that means if we go up one row, go over here, we can't add anything else to our bag. So if we add item 3, we get 120, but we also know for a maximum capacity of 30, there's a combination of items 1 and 2 that'll give us a maximum value of 160, which is more than 120, so we'll stick with that combination over just including item 3. Going to a maximum capacity of 40, we see item 3 has a weight of 30, so 40 minus 30 is 10. So if we do include item 3, we have a leftover capacity of 10. So we'll go up one row, go over to 10. So we see that, hey, if we include item 3, we have a leftover capacity of 10. And what's the best combination of items 1 and 2? What's the maximum value we can get from some combination of those two? It's 60. So actually, we can get 120 plus 60 is 180, which is better than we had previously gotten for that maximum capacity of 40. Lastly, if we go all the way up to a maximum capacity of 50, so item 3 weighs 30, so 50 minus 30 is 20. So we know we can include item 3, and we still have 20 leftover capacity. So if we go up one row over to 20, we see there's a combination of items 1 and 2. The algorithm doesn't track this. It might be just item 2 or just item 1 or maybe both of them. But we know there's some combination where we can extract a value of 100. So 100 plus 120 is 220. We have 20 leftover capacity, so after we do this, go up one row, we have 0 leftover capacity, so we know that is going to be our final answer. And that is all our items as well. It goes up to our maximum capacity, so we know the best we can do is 220. Now, like I said, the algorithm doesn't actually track what is the best actual list of items that gives us this value. It just tells us what this optimal value is. So the for loops here build the table, and then to actually find which items lead to this best maximum value, that's what kind of all this code here does with the while loop. So it starts by taking, we know this bottom right entry is going to be our maximum value. It's going to compare this to the entry right above it. So 220 and 160 are different. So then this implies that we added item 3 to our list of best items. So after we add item 3, the maximum capacity is 50. 50 minus 30 is 20. So we added item 3, had 20 capacity left over. So we'll go up one row over to 100, and we'll do kind of the same comparison. So we know we compare 160. These numbers are different. So we know that we added item 2 to our list of best numbers. So we had a leftover capacity of 20. We used 20, so we go up one row over 0. 0 and 0 are the same number, so we know we did not add item 1. So we know therefore our best list of items is item 3 and item 2. Uh, and in implementing this algorithm, all we're doing is creating kind of this table that's n times w. The dimension is the number of entries are. And each time we're adding an entry, all we're doing is really making one or two comparisons. So therefore, the time complexity of this algorithm should just be O of n times W. Going on to task 2, this was just an extension of the problem we just saw. Let me get the output going. Boom. So like before, I print out a bunch of intermediate stuff. So again, I go into more depth in my written report, but this is just really it's just an extension of the problem we just saw. The extension is now we have two constraints. So before we have a main method, here is what we're trying to maximize. There are different weights and volumes, and then the two constraints on our arrays. It calls our solver algorithm. And the way we really extend this solution, again, we validate all the entry arrays again. That's what those if statements are doing. But the way we extend it is we just really just add a third for loop. The reason we had a third for loop is before we were working with a 2D arrays. Now we're just going to work with a three-dimensional array. But other than that, it's the same thing. We start with a base case and then iteratively and recursively add maximum values for various combinations of items, and eventually we'll get to what our maximum value is, at which point we can walk backwards through it. So again, my report goes through this whole process more in depth, but I did print out some intermediate steps here. So like before, for just the basic knapsack, if you recall, the first row and first column were all zeros. So that corresponded, to choosing 0 items or having a capacity of 0. So the way you can think of this 3D array is a bunch of slices, and each slice is a 2D table, and each slice corresponds to an item. So our first slice would be 0 items. The next slice would be item number 1, item number 2, so on and so on. And each little 2D table slice would be, um, combinations of weight and volume capacities. So again, like I just said, our first slice, which corresponds to no items, means our overall value would be 0. So each cell would just be a bunch of zeros. And from then on, we're going to kind of build our 3D array, much like we just did for the basic knapsack problem. So item 1 is going to have a weight and a volume, and there has to be enough capacity to hold item number 1. So we see all these 0 entries mean, that a weight of 1 and a volume of 1 means item 1 can't even fit in those within those parameters. So what it does is it then looks, we can't add item 1, so it looks to that initial base 0 slice, grabs that 0 value and puts it here. But we see when we get to volumes of 2 and weights of 1, or at least 1, we see that then container 1, or I should say, can actually fit onto our cargo ship. So that means we can at least put container 1 on our ship. Container 1 has a value of 150. So, if the maximum value we can achieve by either choosing 0 containers or 1 container is going to be 150. And then like before, we're going to jump up to the next slice, which corresponds to item number 2. So item number 2, or container number 2, has its own weight and volume parameters. There has to be enough room for it. So we see where all these 150s are. You can see it's kind of this column and these 2 rows here. That means we can't even fit container 2 into them. So the best we can do is just put container 1, which is 150. So it'll check that. We'll see, container 2 can't fit. So jump down to the previous slice, grab that value of 150, and then put it there. But we see when volume gets to 3 and weight gets to at least to 3, then we can start fitting container 2 in there. So it looks like for this kind of chunk here that I'm mousing over, it looks like we can only put container 2 in. So it'll take, the value of container 2 or the profit from it compared to the profit of container 1, which is just 150. Say, hey, it's better to choose container number 2. It'll give us a larger profit. Then when we get to a volume of 5 and a weight capacity of at least 4, then we can actually start fitting containers 1 and 2. And we start getting a total profit of 350. Then we'll jump up to our third slice, which corresponds to container number 3. Again, container number 3 has its own weight and volume requirements. So we see, for, weights of 2 or volumes of 2, weights of 1, we can only fit container 1. So it'll go up here, grab that 150, and do the same thing for these values of 200. So say, hey, we can't even fit container 3. So we'll jump here and grab these 200 values and insert them into our table. Same thing for these 350s. Then if we see that at a volume of 7 and a weight of 5, we can actually fit container 3. So we can fit container 3 and then either container 2 or container 1 or both, and we can get a total profit of 450. Like I said, the algorithm as it's building this table doesn't necessarily track that, but we know container 3 will at least be one of our containers. So like we did for the 0-1 knapsack problem, we know the corner of our 3D array is going to contain our maximal possible profit. What we do is we take that number, 450, we go down 1 on our 3-dimensional array. So that'll be actually to here to this 350. These 2 numbers are different, so we know we added container 3. Let's see. So container 3 has a weight of 4, a volume of 5. So that means the leftover weight and volume should be 1 and 2. So we'll jump down 1 slice, go to 1, go over to 2, and say, hey, look, with a leftover volume weight of 2 and 1, we can actually get a profit of 150. So we'll take this 150, we'll go up 1, compare it here, and see that 150 and 150, these are the same numbers. So we actually don't add container number 2, but we still have a leftover weight volume of 1 and 2. So we'll jump down a slice, but this time to the exact same cell here. Now we'll compare 150, and then I didn't print it here, but there's that 0 slice, recall. So 150 and 0 are different. So that means we did add container 1, or we use container 1 to get to this maximal profit of 450. And we see here container 1, container 3. We see we maxed out on our weight and maxed out on our total volume. And then since this is just an extension of our 0-1 knapsack problem, which was complexity of O of n times W. This is an extension, but now we're just working with the 3D array, so the complexity should be O of n times W times V. So that's my presentation for this code, showing it runs as well as some of its sample output. Again, like I said, I went to a lot more depth about how all this works in my written report, but I was trying to keep this short. So thank you for your time.